Let's take a look at chapter 2. In this chapter that we will introducing you some mathematical foundations. Do not worry about that you will be learning a lot of math, since we will only tell you how to analyze the networks using very basic math. And so you will be introducing different concepts such as graphs, paths, and components. And there are different kinds of a matrix and how to calculate the matrix by multiplications. Okay, so let's dive in this chapter. And these are the learning outcomes. In the first part, it tells us that actually networks are in all different kinds of fields, such as biology, chemistry, computer science, etc. And when we are looking at the network and we're trying to do the analysis for the network, we were looking at the graph theory. We're not talked about too much deeper knowledges about graph theory, but we will tell you and get a sense of what is it about. For example, we were looking at some of the terminologies, matrix. And so matrix can be used to represent networks. We use matrix to draw the diagram. Instead of just saying the diagram, but we'll say graph. We draw a graph, and so to represent the network using the mathematical foundations. One of the foundations is called matrix. And if we wanted to compute, we wanted to calculate the network, we're using matrix algebra. So this is quite useful in the network analysis. Second part, we talk about graph. Just like I said, we draw the network by using the graph to represent that network. And this is the way to mathematically conceptualize the network. So the term graph represents mathematical objects. Here, I give you two examples about mathematical objects. One is graph G, the other is graph H. And we will see in graph G, there are two symbols, V and E. V represents vertices. You can also call nodes or points. E represents edge. You can also call links and the line. In graph G, you will see vertices and the edge. So the edge connects pairs of vertices. And in other words, in a graph G, if there are two connecting vertices, I and J, in the graph G, and there is an edge connecting those two I and J vertices, we could use I and J in a parenthesis belongs using the symbol epsilon, that I and J belongs to the graph G with the edge. And we use I, G, J to say I likes J if G represents the likes relations. There's another mathematical object, graph H. The H also contains some vertices, and we use A to represent a device. In other words, a device means one vertices providing suggestion to another vertex J. The A represents a device, so providing a device from vertex I to J in the graph H. If there is a tie between I and J, we will say I and J has a tie to each other. But since I links to J and it's just right next to J, so I is right next to J, then we will say adjacent. Using the term adjacent, I has a tie to J because I is right next to the J, and by using one edge to link to the J. And we have another term, degree. The degree is the number of the edge incident on a node. So for example, there are two edges, and those two edges are incident upon I. So I links to J, I also link to K, but J and K not necessarily links to each other. Another thinking about the graph is a directional graph or unidirectional graph. Or you could say directional network versus unidirectional networks. If we are in the directional networks, then we will be very cautious whether I links to J or J links to I, since there are different meaning. If I providing a device to J, then J will receive the advice from I. However, if I holds the positions in a company, then I providing a device to J, that means something. And it's totally different if you want to say J providing some suggestion to I, then in the same settings, then that means totally different. The employees providing their suggestion to their boss, and so that means totally different things. However, in the unidirectional network, we only want to know whether there is a tie between I and J. That's it. And there's another term we call reciprocated tie. Reciprocated ties means I and J, J and I exist simultaneously. Another term, reciprocated ties, it actually talks about the pair of vertices. For example, the vertices I and J. If they are in a pair and they have interactions, then we will say they have reciprocated ties. In the third part, we talk about paths and the components. The very important concept in the graph theory is path. Here give you a definition of path. It says a sequence of adjacent nodes. And I have tell you what is adjacent nodes. From I to J, since I is right next to the J. So from I to J, this particular kind of sequence of adjacent nodes we call path. And from I to J means there's a directional sequence. We only go from I to J, this sequence. From J to another vertex, we will never go back to the vertex I. So the path here we says a particular kind of sequence of adjacent nodes. With a directional sequence, the path is never revisits a vertex. If a sequence revisits a node, we will call it a trail. But be noticed that the trail means that the sequence never revisits an edge. For example, here, I goes to J, goes to K, and then go to O, and back to J. J has been revisited, but using different sequence will never revisit an edge. So that's we call the trail. And now you know the path is I to J is a path, J to K is a path, K to O is a path, O to J is a path, and these are all directional sequence, particular kind of sequence of adjacent nodes, and you will never revisit a vertex. Now let's move on to take a look at walk. Walk is pretty free. It says any sequence of adjacent nodes without restrictions. So you can walk from I to J or J to I, as long as that these two nodes, they are links with each other, and the I right next to J. And J links to K, so these two, you can walk from J to K, K to J. And so now we can conclude that every path is a trail, and every trail is a walk. Now let's look at the geodesic distance. And we can simply say a distance. The length of walk is defined as the numbers of age it has. In other words, the walk including either path or trail. So geodesic distance here, that we were looking at the shortest distance from I to J or J to K. Or in a graph, there will be a lot of the shortest path. Then we will say that's the geodesic distance. That's their shortest path. If we have a longer geodesic distance, it implies us that it will take some time from I walk to J. So here gives you the example, virus infection network, where you expect a longer distance in the network or shorter. And how about the Gaussian network, where you expect a shorter distance or longer distance in the Gaussian network? These two examples also help us to differentiate these two terms, path and the trail. We assume that the virus, when one person gets infection, and the virus will not go back to the person because the person will produce the antibiotics inside the body. So this example helps us to explain the path. However, the Gaussian network is very likely when I tell some Gaussian to J, but it's very likely O also tells the Gaussian to J. So this example tells us what the trail is about. The components is defined as a maximal set of nodes. And in the components, every node can link to each other by some paths. Here, the weak component is in a unidirectional network. However, in a directional network, you could find a strong component. If you add a node to a component, to a set of nodes, every node can still reach each other, then we will still consider as a component. If you wanted to take one node out of the components, it's very likely that we will produce more number of the components in a network, or the network will break. And here we say that the nodes that you remove probably is a cut point. And the edge that links from one component to another will be we consider as a bridge. For example, if we wanted to remove J from this component, KOJ, then we will see that all of the network will break. So J will consider as a cut point. However, I will not consider as a cut point. The edge, or we call the bridge from J to K, will also break in this network, and the J to O will also break. So the bridge from O to J, or the bridge from J to K, these two bridges or two edges, they are broken. In a network, usually we will put a value besides the edge, so that we know there's a value in this network. You will have a quantified numbers to represent the tie or the closeness of the tie between I and J, for example. The dyadic cohesion in a value network means there are two adjacent nodes, and they are closely linked to each other. And you wanted to know in the entire network, what is the degree of cohesion in this network. In the fourth part, we are looking at adjacency matrices. So adjacency matrix is a matrix. When we wanted to draw a graph for a network, we could also using a matrix to represent a network. So rows and the columns are all represent nodes. For example, this is a matrix, and there are 5 nodes. And each one of the nodes put in the row and the column. So if there's an entry, for example, the first entry is 0, in this row and this column, then we will be able to represent a tie from this I row to the j column. So xij equals to 1 or ixj equal to 0. For example, this one means xij equals to 1, and this one xij equal to 0. If 0 means there's no tie from I to j. So from Holly to Brazil, there's no tie. They do not link to each other. The direction is important. We always read from row to the column. So from Holly link to Brazil, Holly link to pen, xij equals to 1, Holly link to Pat, the xij also equals to 1. We may also wonder what's going on with here, having a 0 value. It's very likely there's no link, but it could be a missing value since Holly didn't report himself. So you could see this diagonals is all put 0 since it is meaningless if you wanted to have a self loop. What would be it likely if you link to yourself? So there's no meaning. But it's very likely Holly didn't report her relations with Brazil, so there's a missing value, and we put 0 here. Then you may ask, there's a big difference, a very big difference, that we do not want to self-loop, or there is actually a missing value. You can leave a blank instead of put a 0 because 0 since there's no tie instead of missing value. There is another type of matrix we call proximity matrix. This matrix is a general category of matrices, including geodesic distance matrix, or you could simply put distance matrix. You could measure the closeness or similarities of pairs of entities or a pairs of nodes. Contrarily, you could also measure the farness or dissimilarity of pairs of entities. Ways and modes. Very often when we see a matrix, it's a one-mode matrix. So you will see like this square shape in the matrix. It is one mode because the rows and the columns are both refers to the same sets of entities. However, we could looking at the two modes matrix. The two-mode matrix will refer to two different sets of the entities. For example, we could take a note for those people what are the courses they take in this semester. Then we could put in a matrix like this. For different persons, they are taking different courses. 1 refers to yes, 0 refers to no. And this two modes matrix, we could also using another term to represent this matrix that we call affiliation matrix. For each one of the person, they affiliated with different courses or different events from event 1, event 2, or event 3. So the way equals to dimension, usually 2 because we have rows and the column, rows and the column. So we have two-dimensional matrix, and so that's we call the way. But the mode refers to numbers of kinds of the entity. For example, here only have single entity, that is the name. But this matrix has two different kinds of the entity, so we call two-mode matrix. One is the name, the other one is the course or the event. Now let's take a look how to calculate the matrix. We're using the multiplications. For example, A and the B represent two different matrices, A matrix, B matrix. Then the product of A and B refers to C. So the product's results of matrix A and B is C. There are something I want you to keep in mind is the number of columns in A equals the number of rows in B. And so if we have that conditions, we do the calculations for the products A and B will not be equal to the product of B and A. Another thing is that we can use in the matrix multiplication to construct a compound social relations. What does that mean, the compound social relations? Here, give you an example. The F refers to a friend of relations, and the E represents the enemy of relations. If we using FE, that means enemy of a friend of. So here we have vertex I and the J. Feij larger than 0 means the number of I's friends who have J as an enemy. You can replace I as me. I have several friends within those friends, and I consider them, some of them are my enemy. So I has at least one friend for whom J is an enemy. I have at least one friend, and that friend probably is my enemy. J is the enemy of I's friend. So J, in another word, will be my enemy. Let's look at another relation, FF, friend of friend. FFij larger than 0. It means I have at least one friend who consider J a friend. Again, we could replace I as me. I have at least one friend, and that friend probably is my friend. And we could also use another formula, FFij equal 3 or F3. This means the number of walks from I to J that are of length 3. For example, here, there are a number of walks from I to J, I to K to I to J. One way to walk from I to J, or I to K to M to J. This is also another way that you walk from I to J. The length 1, 2, 3, 1, 2, 3. So the number of walks from I to J that are of length 3. Let's look at the very interesting relations in the social theories. There are 4 different kinds of relations, and the results are different too. For example, the first one, FF, the friend of my friend, is my friend, of course. The next one, FE, the friend of my enemy is my enemy. It makes sense. But let's look at the third one, EF, the enemy of my friend. And the outcome will be my enemy too. The last one, double E, the enemy of my enemy. The outcome is very interesting. It will become my friend. So that is a very interesting part in the social theories, and we could find those 4 different kinds of relations in the theories. One other common use for matrix multiplication is to measure overlaps in a social neighborhood. The overlaps means we could find the people, each other, each one of us, we know each other in common. So in the social neighborhood, since one not is my neighbor, so we could find the network in an acquaintanceship. Acquaintanceship represents as a matrix A. For example, this matrix. When we transpose the matrix, it will look like that. For every pair of actors, how many people they knew in common? In a directional network, we use matrix A to be multiplied by the A transpose. We could get the number of outgoing ties that each pair of knots has in common. Again, in a directional network, the transpose A multiplied by the matrix A could get the number of incoming ties they have in common. So these two different measures will tell us how many people they knew in common in terms of outgoing ties or incoming ties. Okay, that's the end of the chapter 2.